Hey guys, if you're watching this, we've hopefully recently wrapped up the section on tangent planes and differentials, and we're ready to move on to section 14.5 in Stewart. This will be the first day of our chain rule section. As I mentioned you guys numerous times before, big goal for us is going to be finding ways to pop up stuff from old classes into higher dimension. So let's go ahead and get started here and working on doing that with the chain rule. Now, before I get going, let me get my pen straight here. One thing I'll want to recall for us is what is the chain rule in the first place. This is our way that we deal with taking derivatives of compositions of functions. So back in Calculus 1, you guys probably saw a formula that looked something like this. Your derivative of f of g of x. This is the same thing as the derivative f prime of g of x times g prime of x, or more commonly, the derivative of your outside function times the derivative of your inside function. Okay, I'm not going to bother with examples of this. I'm sure you guys are pretty familiar with it at this point. One thing that I will introduce for you guys is some alternative notation for this that you may or may not have seen before. It'll probably come in handy today with how we're going to phrase the chain rule. What I'm going to suppose is that y is this function f of u, and then, I've also got this function u is equal to g of x. Then another way to phrase my chain rule is going to be the following. I'm really looking for dy dx in this case, because if you take that composition, you're looking at f of g, your function variable, one of the names is y, and your input variable is x. So this is the same derivative as what we're looking at up top. This can be formulated as dy du, let me make it clear that that's a y here, times du dx. So what's really happening is for dy du, that's the derivative of y with respect to u. You'll notice that's the derivative of our outside function here. And then for this du dx, well, u was really g, and the variable there is x. So the derivative of u with respect to x is really the derivative of our inside function. So both of these expressions of the chain rule, they're functionally equivalent, just one's in prime notation and then one's in this dy dx notation. Okay, so be prepared to look at something that's kind of similar to this guy in a little bit. Now, at any rate, that's our single variable recap. What about now? What kinds of functions are we looking to take the derivative of now? Well, here's my big old motivation for today. Suppose that I've got a function like f of x, y. Okay? Suppose I've got f of x, y, and this guy is composed with two other functions, okay, namely x of t and y of t. Hopefully we can already see where the problem is with us being able to use old methods. This guy takes two inputs, whereas before when we were in single variable calculus, our functions only took one. So, there's really one place that we could worry about sticking functions when we were taking a composition. Now there's two. So, how do I handle this? Well, before I take a look at that situation directly, I'm going to go ahead and pose the question of, well, what might such a composition look like? If we switch over to this next slide here. Here's a very practical example of a situation in which we're performing this composition. What I've got here up top, you see the contour map, this is a map of a mountain up in Virginia that I've gone hiking on before. It's called Angel's Rest. We can see some of the neat features on the contour map, like I've mentioned to you guys in class before. Whenever the lines are really, really bunched together, that means it's super steep. Whenever the lines are a little bit further apart, kind of like at the base of the trail here and up at the top of the mountain, whenever the lines are far apart, it means that it's a little bit flatter. So hopefully you guys could notice that here's probably the really crappy part of the hike, so they had to zigzag back and forth rather than going a straight path. But at any rate, here's how this fits in with my composition here. I'm going to view this mountain as a surface, okay? Now, we've talked about graphing functions before. If you graph a function of two variables, you typically get a surface back where we interpret z equals f of x, y. Z gives you the height. So I can think of this as maybe a surface where if I plug in a given xy coordinate, given longitude and latitude, it'll spit back out a height. And this mountain is just the graph of that particular function. Now, that's my function f of x, y. What about this x of t and y of t? Now, we've mentioned for vector-valued functions that if you think of some sort of vector-valued function r of t, that's the vector x of t and y of t taken together, then that'll give you a curve in space. That's kind of like this red line that's on the map here. And you can kind of view this as, plug in a t, you'll get an x-coordinate and a y-coordinate, so longitude and a latitude. At a given time, you're at a particular location on this curve. Where the composition comes in is this. If you plug in a given longitude and latitude to the function telling you how high up you are, that's like looking at the longitude and latitude on the map and wondering, how high in elevation are you? Now, if I actually take that composition and interpret it as a single variable function, I get this thing that's on the very bottom of my graph here, right? I plug in a time, I get my elevation. So, this is just one example of a situation in which we would be able to look at a case like this, where I'm taking a composition. And if I'm interested in taking derivatives, this is, another practical question to ask in this situation. Derivatives tell you slope. If I'm asking for the derivative of this function, I'm really asking how steep my elevation is changing, or basically how crappy the hike is, right? So let's look at a similar example to this particular case. I'll switch over to the next slide. Let's take a very simplified model of that situation that we were just looking at. I've got a function, f of xy equals x squared plus 2xy. This is going to model a surface that a particle is traveling along. So, this surface that you're graphing, this could be a very simplified mountain to hike up, and, the particle is your hiker. In my xy coordinates, if the xy coordinates of my particle are given by this r of t function, here I'm specifying my longitude and my latitude, what I want to do is find the rate of change of the particle's height with respect to time. So there I'm just asking for something to tell me how steep am I at a given time. Okay, well, there's a couple different methods that we could try to use to approach this problem. I'll go ahead and note method 1 for approaching this is, well, we can cheat and think of it as a single variable problem. First off, we could go ahead and substitute my x and y into my f, and then just take a regular derivative, right? Take a derivative. Okay, so here I'll go ahead and note, if I take f of x of t, y of t, this composition is having me substitute 2t in each time I see x, and it's having me substitute, let me get this guy in here, it's having me substitute t squared in each time I see y. So I can go ahead and kind of consolidate this. We'll think of this guy as basically f of t now. Once we perform this composition, this turns into a single variable function. We'll get 4 t squared plus 4t cubed. I'll scroll down a little bit to give myself some more room. In this case, my derivative is pretty easy to knock out with power rule. We'll get 8t plus 12t squared. So this is going to give me my rate of change of this particle with respect to time. Now, a comment that I will go ahead and make. This isn't always quite so cut and dry because, maybe we don't have explicit functions everywhere. Maybe we're taking, different bits of our data at different times. So maybe it's not always the easiest to directly take this composition that we did in this particular question. Another potential issue with substituting stuff in as being a primary method is, well, what if I have multiple paths that I'm interested in here? Okay, so I'll go back and look at this original problem statement. I gave you this particular r of t to substitute into this function. Well, if I needed a slope for every new path that I tried to shove into this function, I'm doing a composition of derivative every single time. Maybe it might be nicer if I could just worry about taking individual derivatives related to the inner function each time and not have to always, worry about that initial composition first. So I want to give you guys an alternative, and we'll just slip over to the next slide here. Alternatively, we can try the chain rule. So I have this already written out for you guys. The chain rule, case 1, the case that I'm referring to here is f is a function of two variables, and y and x are both functions of a single variable. In this particular case, will it z equals f of xy be a differentiable function of both x and y? We'll name x some single variable function and y some other single variable function, and assume that both of those guys are differentiable. If that's the case, when we take this composition, z is going to be a differentiable function as well, and we get this formula down here, which is basically the higher dimension analog of what we saw before. Now, a couple comments. You may notice, if I look at each of these individual cases here, that these kind of look a little bit like my chain rule. Okay, now that's obviously no coincidence. We'll talk a little bit more about why that happens later. But what it comes down to is basically that we're getting ultimately some rate of change of my function z that is coming both from a rate of change based on what happens when I alter x, and a rate of change that also comes from what happens when I alter y. So the total of those two together is going to influence the overall change in my function. Another thing that I do want to emphasize in this formula, that it looks close to but not quite like chain rule in each of these places. Remember, we've got the curly d to represent that we're talking about taking partial derivatives, and we've got a regular d to represent that we're taking single variable derivatives. Since z is a multivariable function here, it requires partials. Since x and y, since both of those guys are single variable functions, we write the derivative symbol there like normal. Okay, so that is my multivariable chain rule. Let's see if we can try that last example one more time, but we'll do it the new way. Okay, so we'll try basically what I'll call method 2, which is my chain rule here. We'll try that to tackle this problem. Okay, now as a refresher, the formula from the last slide is basically as follows. We needed that my df dt was going to be given by a partial of f with respect to x times dx, let me watch my handwriting here, dt plus a partial of f with respect to y times dy dt. Now in this particular case, if I wanted to name what each of these functions is, well, we've got that my f of xy is, as explicitly stated up top, is x squared plus 2xy. My x functions and my y function, I'm going to need to take the derivative of those, but what are they? Well, here my x and my y, these are really the component functions for this this vector that I've got right here. Okay, we'll assume that the first component is my x function that I am plugging in up here to f of x, so this guy will be 2t. And my y component, my t squared, that's going to be the function that I'm plugging in for y of that curve. So that'll be my t squared. Now if I want to go ahead and compute this, okay, and actually crank this guy out, let me scroll down so I have room. I am going to go ahead and find my cursor here and just take the required partials that I'm looking at. Okay, so my partial of f with respect to x, if I look back at this function, we're going to be getting 2x plus 2y for that part. My partial of x with respect to t, this is basically just going to be x prime, so there that's going to be a 2. My df dy, this is a derivative of f with respect to y. Don't forget, x acts like a constant, so that first term drops off. Your partial with respect to y is then just going to be 2x, and your dy dt is basically y prime, so you have to throw a 2t on here. Now, I will note this looks a little bit different from what we saw before because, you know, I asked you guys for df dt. It's basically f prime of t. We've got x's and y's mixed in here. So we'll go ahead and make the side note for a, I'll put this in quotes, final answer. You basically want to sub in any x's and y's that you have. Okay, so I'll go ahead and do that. My x of t function over here was 2t, so this is 2 times 2t. My y function was t squared, so this is 2t squared. Again, my x function was 2t, so 2t goes here. And then I have this 2t on the end. And if you want to, the rest of this is just going to be cleaning up whatever you have algebraically. So I'll have an 8t squared on the end. I've got an 8t plus 4t squared plus 8t squared. Alternatively, this is 8t plus 12t squared. Okay, so ideally, if I pop back a couple slides, let me just go ahead and see if I can pull that guy up. We came down to 8t plus 12t squared on the last slide. Okay, so both methods, it doesn't really matter which one you're using, both of them are going to end up giving you the same result. Okay, now let me go ahead and move back on from this example, just to very briefly talk about why the heck this works in the first place. Because I just randomly gave you guys this formula. I usually don't like doing that without providing at least some minor bit of justification. So here's kind of the rough idea of my proof. This is based off of my differentials that we talked about in the last section, right? If you guys don't recall the formula, here's the formula that I'm referencing. We said that dz was going to be very, well, not roughly equal to, but dz was going to be equal to your x partial times your dx, your differential dx, plus your y partial times your differential dy. In other words, the approximate z change in your function is based off of some change happening in the x direction plus some change that's happening in the y direction. both of those are going to have an influence in the output of your function. So here's what this very roughly implies. I'm going to think about this in terms of actual change of each of these variables, since I'm dealing in a rough equality. What this is suggesting is that if you want an approximation for delta z, I won't write a true equal sign here, write one of these squiggly ones that suggest that it's an approximation. My delta z is very roughly going to be your x partial times delta x plus your y partial times delta y. I haven't really changed anything here. I've just shifted from my differential symbols to these true change in each variable symbols. What I'm going to go ahead and do once I'm at this situation is think of the following, right? I've got these functions, f and x and y. Really, z is another sort of name for f in this particular situation. Z was whatever the output was when you plugged in x and y, and f was the function you were plugging x and y into. So do keep that in mind. If I've got this chain rule situation like we've been talking about, we're basically assuming that x and y are functions of some sort of variable t. Well, what happens if I go through and I divide everything in this rough equation through by a change in time, right? Well, I'll go ahead and do this here. Here's my delta z. I'll divide that by delta t. I'll divide this term through by delta t. And I will divide this term through by delta t. You notice this looks actually pretty close to what we've got for our chain rule formula. The only catch in this proof, and this is why I'm calling this the idea of the proof and not a formal proof itself, you kind of have to be a little bit careful with actually setting up your limits here. And, whether your limits actually exist in the first place, right? What this is effectively stating, assuming, you take a limit across the whole thing as delta t goes to 0, this will look like the derivative dz dt. The thing multiplied by fx is going to look like the derivative dx dt, and the thing multiplied by the y partial is going to look like the derivative dy dt. And this is basically the chain rule formula right here once you take that limit. So, rough justification on where this formula comes from, why it works, but I'm sure you guys are probably a little bit more concerned, not necessarily with the why, but on how we use it. So let's see if we can try at least a couple more examples. Let's go ahead and let f of xy be x squared plus y squared. I'll give you guys x is the sine function, y is the cosine function. Let's go ahead and find that derivative of the composition, df dt, using both of the methods that we've looked at before. We'll try the substitution, and we'll also try the chain rule method. Okay, so if I try this with direct substitution, what this is actually having me do is, well, take a actual derivative of whatever happens when you take f and, plug x of t and y of t in. Okay, and just be careful that you got your order straight here. Well, this means that I really want a derivative of what happens when I plug these functions in. Well, I'm squaring sine of t. I'm also squaring cosine of t. Now, we could directly take care of this using single variable chain rule on each of these terms, but I would prefer to work smarter rather than harder. Most of you guys will probably recommend that this is a cute little Pythagorean trigonometric identity here. If you take sine squared of t plus cosine squared of t, that's the function 1, the constant function, and your derivative of any constant function is going to give you 0 back. So this is one method to be able to tackle this problem. Let's try this with my chain rule instead. So there, my df dt, this looks maybe a little bit different from what we were dealing with before, but in this particular case, keep in mind, f of xy, this is a function of two variables. We usually interpret the output of this as a height z in 3 space. So for us, just like y and f were interchangeable back in Calculus 1, z and f are going to be interchangeable for us now. So df dt, dz dt, for us those are going to be the same thing. Here, this is going to basically be df dx times, oops, these should be my curly Q partials here. I'll be a little bit more careful about that. Df dx times dx dt plus df dy times dy dt. Well, just as a refresher, since I'm going to have to scroll down here in a moment, I will copy over these functions just one more time so I have them for reference. Remember, f was x squared plus y squared, x of t was the sine of t function, and y of t is the cosine of t function. Okay, now let me go ahead and scroll so I can give myself some room. Here, if I'm going ahead and computing these partials, you notice df dx in this case comes out to 2x. Dx dt in this case comes out to cosine of t. Df dy comes out to 2y. And dy dt comes out to minus sine of t. Now I mentioned before, don't forget to sub in your x and y to get a final result. If I go ahead and do that, 2 times my x is going to be 2 times sine, if I perform that substitution. And over here, 2 times y is really going to be 2 times my cosine. So here's the rub. I mentioned before you should expect to get the same thing both times. Well, we've got a positive sine t cosine t term, and you have got a negative sine t cosine t term. So both of those cancel out, and we get the same 0 that we got in part A. Okay, now I can kind of imagine the complaints now. The first method when we tried this, if I go ahead and scroll up a little bit, this was probably a little bit more intuitive for most people, especially since, you know, a little bit less writing than what we had to do this time. But as I mentioned before, depending on the way that you collect the measurements for your functions, direct substitution isn't necessarily always easy to do. So let me show you guys an example that kind of highlights this. We'll click over to the next slide. Suppose that I've got my 2 functions that I'm using as inner functions, x of t and y of t, and that we've got some sort of an outer function such that my partial with respect to x at the point 416 is a negative 3, and my y partial at the same point is 2. What I'll go ahead and do is ask you guys to evaluate df dt at the point t equals 1. So if you aren't entirely clear on this notation, or if you haven't seen this notation before, I'll go ahead and rewrite this. I just wanted to make sure you guys had seen this in case it pops up in the book anywhere. The line, the vertical line, just means restricted to whatever you specify down here. So in this particular case, I'm saying df dt restricted to the point t equals 1. Well, if you restrict a function to a particular point, you're really just plugging that point into the function. So another way for me to go ahead and rewrite this guy is just to say evaluate df dt at t equals 1. So you guys hopefully learned something notation-wise today. If I want to compute this derivative, right, I don't have an f function here for me to be able to plug an x of t and a y of t into. So method 1 is just totally shot. A way that I could maybe think about analyzing this is, in our hiker situation where we were on the mountain, this is sort of like knowing where your path is, okay, being able to specify your path, but, somebody decided to collect some surveying information on steepness of the hill independent of knowing your path, right? So they've surveyed this mountain. They kind of know how steep it is in different directions. That's on record. But the map makers don't know your path. So we're going back to figure this out independently. Okay, now for me to tackle this, kind of like before, if I'm assuming that I'm applying chain rule, I will need my formula, df dt. This is my derivative of f with respect to x, dx dt, plus my partial of f with respect to y times dy dt. If I'm worried about this thing at t equals 1, well, what's with all this 416 stuff? One thing that I'll note, which is why all of this is given to you in this particular problem, that t equals 1 time corresponds to, if you actually plug it into your x and y coordinates, this corresponds to your point, 4 times 1 cubed, which is 4, and 16 times 1 squared, which is 16. So, if you are plugging t into one of the functions involved in here, you plug in t equals 1. On the other hand, if you see xy coordinates that are floating around here, you are going to need to plug in this point 416, because those are the x and y values that you get by plugging in t. So let's actually take a look at this here. If I want to restrict this thing to t equals 1, okay, and if I want to restrict this entire thing to t equals 1, well, I need an f partial with respect to x at the associated point. So this is basically going to be this fx partial that I'm giving you guys here, minus 3. I need my derivative of x with respect to t. Well, this is actually a derivative that we can take. We're going to want 12t squared, but again, we are assuming that we're restricting this to t equals 1. Df dy, this is me wanting my f partial with respect to y when t is 1, but when t is 1, it's really that point. This means I want my fy partial, which we have set up here, comes out to 2. And I also need my derivative of y with respect to t, which that's another derivative we can easily take. I get 32t here, but again, this whole thing I'm assuming that I'm working with where t equals 1. We've already technically plugged in the places where we see x's and y's. I just need to worry about substituting t equals 1 in for t where I have it. So here I'll get basically minus 36 if I combine those. Multiplying by 1 doesn't change anything. Similar deal over here. I'll get a 64 if I combine those. Plugging in t equals 1 doesn't change anything. So if I add both of these guys together here, should give me, what, 28? Okay, so whatever units that we're associating with this particular example, you could append those if we were given units, but my df dt at this particular t value is going to be 1. Okay, now with all of that said, I wanted to at least give you guys a brief question to throw at me on your return whenever we come back on Monday. So I'll go ahead and just give a super fast example here. So I'll just assume f of xy, this is x squared y. I'll let x of t just be t, and I'll let y of t be 2t. So I'll just go ahead and ask you guys, use my chain rule to find my derivative df dt. So just show me that you guys can apply the formula in a really basic way. If anybody has any questions for me, I'm willing to take stuff by email if I get a chance to get at it. You're also welcome to come find me later in the week. And don't forget, this was the first day of a 2-day section, so you're also welcome to bring stuff to class the next time that you see me.